I hope you can see my slides.
Yes.
Yeah, good. So I was saying that we have two main objectives today to discuss about integrals involving trigonometric functions, and then to discuss integration method by partial fractions decomposition. So trigonometric integrals involve the combination of the 6 basic trigonometric functions. So we have the sine function, the cosine function, the tan function, the secant function, the cosecant function, and cotangent functions. So in this section or in this lesson, we'll be discussing integrals involving any of these 6 basic trigonometric functions. So from the elementary definition of integrals, where we started from, we say that when you differentiate a tan function, you get a sec squared function. So which means the integral of a sec squared function gives you a tan function. And then if you are dealing with the indefinite integrals, then you add a constant of integration c. So the integral of sec squared x dx is the same as tan x plus c. But then the functions we'll be dealing with or will be meeting along the way will not be involving these standard integrals, like sec squared to give you tan plus a constant. So the first group of integrals that we want to discuss are integrals of this form: sine power mx times cosine power nx dx, where this m and n are whole numbers or positive or non-negative integers. The easiest way or the easiest case to solve problems of this form is when one of the two powers, m or n, is an odd number. So if you find either m or n is an odd number, then we make use of the substitution. We make use of the identity that sine squared x plus cos squared x equals to 1. Then we use the substitution method to evaluate the integral. So we'll discuss or we'll give examples to illustrate what you need to do for different cases of the values of the powers m and n. So let me know if I can scroll down. So the key thing, what you need to note down here is that the integrals of the main class of integrals we are discussing are integrals of this form: integral of sine power mx cos power nx dx. So this is the class of functions we are dealing with. So we give an example which involved m to be 3 and n to be 0. So remember, this general form we are saying is sine power m times cosine power n. So in this case, when we have the integral of sine power 3x dx, m is 3, n is 0.
Excuse me, sir.
Yes?
You have an echo in your sound.
It's not from my end. Probably there's one person who has two gadgets that are making noise. So if 2 or more people are seated together, please mute all the other gadgets we're using. Those are the ones causing the echo. I hope I'm clear now.
Yes.
Yeah, you're clear.
Yeah, good. So the first example is to evaluate the integral of sine power 3x dx. So in this case, the value of n is 0. So cos x power 0 is just 1. So when one of the powers of the sine or cosine function is an odd power, then you remember that sine squared x plus cos squared x equals to 1. So you split this power 3 in terms of product of two functions of sine. Split sine power 3 as sine squared and another sine function. So you see sine squared times sine will still give you sine power 3. So when you split this odd power so that we have two products, where one will be an odd power, just sine power 1, and another one will be an even power, sine squared, then you make use of the relation sine squared x is 1 minus cos squared x. So with this relation, you substitute where the sine squared by 1 minus cos squared. So this integral will now be sine power 3x dx equals to sine squared x sine x dx. Then in the place of sine squared, you replace by 1 minus cos squared x. And then this other part remains to be sine x dx. So we have not changed the integral, it's exactly the same integral, but then now we are making use of this identity to enable us to reduce or express the integral in a form which is simpler to integrate. So with this new expression of the integrand, then you make use of the substitution u equals to cosine of x, because you know that when you differentiate a cos function, you are going to get a sine function, which will cancel out with this other sine function. So fixing u equals to cos x, then the u will be negative sine x dx. When you make dx the subject, you can say dx is the same as minus du over sine x. So when you replace in this integral the place of dx by negative du over sine x, the sine function and sine function cancels out. So you will remain with negative integral of, so the place of cos you replace by u, so cos squared will be u squared, and then this other part will just be du, because this negative is from this part here. So you see, then this is now an integral which can be solved by the power rule method. So integral of 1 du is just u. Integral of u squared is the same as u power 3 over 3. Then when you multiply by the negative sign, so this will be negative u, and then minus minus is plus. So plus u power 3 over 3, then plus the constant of integration c. And then as we were discussing previous methods of integration by substitution method, you remember that once you have found your answer in terms of this new variable u, the final answer should be re-expressed back into the original variable that was in the question. So where there's u, you replace by cos of x, and therefore the final answer will be cos cubed x over 3 minus cos x plus c. So that's what we do. So the key thing here is when the power of any sine or cosine is odd, you make use of the identity cos squared plus sine squared equals to 1. Then you split the odd power as a product of two functions, where one will have an even power, another part will have an odd power, and then you make the substitution accordingly. I hope that example is okay.
Yeah.
Good. Then next example.
Repeat.
So, before we give the question, before we give the next example, we discuss the different cases. Of this integral involving sine power m times cosine power n. So there are three possible cases. One case is the power of sine function is an odd number. So when the power of sine function is an odd number, so any odd number can be written as 2k plus 1, where k is an integer. This is a general way of expressing an odd number. So if m is 2k plus 1, then we usually rewrite this sine power m as 1 minus cos squared x power k times sine x. Then this integral will now reduce to this form. Then with this form, you make the substitution u equals to cos x. What is inside this bracket from the identity cos squared plus sine squared equals to 1 is what you fix as your u. And then from there, you do the usual process of integration by substitution method. You will find you will transform your integrand into a form involving only the variable u, where once we have done that transformation fully, the new integrand will be solved by using power rule method. Then you can find in some cases the power of cos function is an odd number. So in similar case, when the power of cosine is an odd number, you split the cos power nx as a product of two functions, where one function will be an odd function just involving the cos x, and then the other part will be involving a cosine function raised to power or an even power. Then the even power part is the one that will help you now to use the identity cos squared plus sine squared equals to 1. And then you retransform your integrand as a function of sine and cosine. But then now, in this case, what you substitute as your u will now be sine x, what is within the bracket from the identity cos squared plus sine squared equals to 1. So once you have fixed your u as sine x, then you can find du, and then your du will help you to transform the original integrand in terms of this new variable u, which you should be able now to solve by the power rule method once we have done the full transformation. So when both m and n are odd numbers, then you can either pick it from case 1 or case 2. So there's no problem there when both of them are odd. When either of them is odd, then you can, if m is odd, then you pick case 1. If n is odd, then you pick case 2. But if both of them are odd, then you are free to pick either case 1 or case 2 to do the transformation. At the end of the day, you'll get the same answer. But then there's the third case where you will find that both the powers of m, powers of sine and cosine are all even numbers. So when you meet such a case where both the powers of sine and cosine are even numbers, then we make use of the reduction formulas to simplify the integral. We'll give an example to illustrate what that one means. So before we go to example 2, what you should actually see from these 3 different cases when you are dealing with the integral of sine power m times cosine power n is that when any of the powers is an odd number, then you recall the identity cos squared plus sine squared equals to 1 is the one that is going to help you to transform your integrand into a form which is easier to evaluate. And once you have identified that one of the powers is odd, then split that term. If it's a sine term, split it as a product of a sine power an even number times sine x function. Then from the even part is where you'll apply the identity cos squared plus sine squared equals to 1. If the odd power is on the cos function, then you split the cos function as cos power an even number times a cosine function. Then the one that has an even power is the one that will help you to transform after replacing or using the identity of cos squared plus sine squared equals to 1. But the case of both powers being even is where you'll need to remember the reduction formula to do the simplification. So this example 2, where one of the powers of the product of sine and cos function is odd, and then the other power is even. So when any of the powers is odd, then you are lucky and the problem is easier to solve, because what you are going to use to transform the integral into solvable form is just the identity you always know, cos squared plus sine squared equals to 1. So in this case, sine power 4x, cos power 5x dx, because the power of cosine is an odd number, then you split this cos power 5 as a product of two functions. One of them is cosine function, and then the other one will be cos power 4. So it's as when the power is an odd number, rewrite that as a product of two functions, where one of them will be that same function to power 1, and then one from the original odd power, which will give you an even power. So this will be sine power 4, cos power 4x, then cosine x dx. So it's the same function, but we are now just splitting this part to enable us to transform the integral into solvable form. So then now this remains to be sine power 4x. Then this cos power 4x can be written as cos squared times another cos squared x. So that's why we are writing this one as a place of 1 minus sine squared x, the same as cos squared x. So cos squared x times raised power 2 gives us the same cos power 4. So that's why you have this expression here. Then you still retain this cos x dx. So once you have done that transformation to that level, then what is inside the brackets from the identity cos squared plus sine squared equals to 1, that is what you fix as your u. So you say let u be this sine part, so u equals to sine x. Then from u you can get du, which will give you cos x dx. Then even from the structure of the integral directly, even if you don't make dx the subject, you clearly see that the place where we have cos x dx can be replaced by du. So which means this integral will be sine power 4. And then because sine is u, then it will be u power 4. Then into brackets 1 minus sine squared, and u is sine, then it will be u squared. And then this square here, then you multiply by du. Du is the part which is cos x dx. Then this is a very easy algebraic expression which you can get the square. So when you square this, you get 1, then minus 2u squared, then plus u power 4. Then when you multiply by u power 4, you get u power 4 minus 2u power 6 plus u power 8 du, which is now a very easy integral to evaluate because you're just going to apply power rule. So when you apply power rule to each of these three terms, we'll get u power 5 over 5 minus 2u power 7 over 7, then plus u power 9 over 9 plus c. And then always remember that when you are using u substitution, your final answer should be in terms of the original variable. So you recall that your u was sine x, so which means then this first term will be sine power 5x over 5 minus 2 sine power 7x over 7, then plus sine power 9x over 9 plus c. So this will be the final solution. So these are the, just as a recall from what we did previously in class, these are the reduction formulas involving sine power n and then cosine power n. So these reduction formulas usually help us to deal with the integrals where both powers of the sine and cosine function are even. So the next example is to evaluate the integral of sine power 4 x dx. So here, when you from this formula 1, which is the reduction formula for sine power n x, is the same as -1 over n sine power n minus 1 x cos x plus n minus 1 over n integral sine power n minus 2x dx. So when we have to integrate sine power 4x, so it means that the first step in this reduction formula, where is n replaced by 4. So when you replace n by 4, the first step will give us -1 over 4 sine power 3x cos x plus 3 over 4 integral of sine squared x dx. So that is step 1, applying the first equation of the reduction formula for sine power nx. Then, because this other part also involves a power of sine function, then you use the same formula for n equals to 2. So the integral of sine squared x dx will be -1/2 sine x cos x plus 1/2 integral of 1 dx. And the integral of 1 dx is just simply x. So when you multiply by 1/2, we'll get 1/2 x. Then when you combine with this other part, this will be our integral for sine squared x dx. Now, in this equation 3 and this equation 4, the answer in equation 4 is replaced in this part for equation 3, now to get the full expression for the total, the full integral. So we'll have -1 over 4 sine power 3x cosine of x, then 3 over 4 multiplied by this expression. And when you do that, 3 over 4 times -1/2 will give you -3 over 8. Then this is sine x cos x plus 3 over 4 times 1 over 2, the same as 3 over 8x, then plus c. So therefore, this will be the full integral. But then there are many ways of rewriting the trigonometric terms. Like if I have sine x cos x, you remember the expression sine 2a is the same as 2 sine a cos a. So there are many other ways of rewriting the same expression. So this is another form or another way of rewriting the same answer. For someone who picks this as the sine power 4x is the same as sine squared x times another sine squared x. And if you recall what you did in class, the way we deal with the integration of sine squared x by using the expression 1 minus cos 2x over 2, then you should be able to see where this answer is coming from. So a person who pick it from that point of view on how to express sine squared in terms of cosine function, and then multiply sine squared by sine squared to get sine power 4, and work out the solution to get this expression, is still okay. Or if you want to apply the reduction formula and get this expression, or this expression on this expression, when you simplify, you will find that they're exactly the same thing. So this is what you're saying, that you recall sine squared can be written in this form, cos squared can be written in this form. So where sine 2x can also be written as this expression, and also cos 2x can be written in this form. All these identities or all these relationships, we derive them in class, so they should not be very new to you. So the integration of sine squared x dx, if you remember what we did in class, if you apply this definition of sine squared x, you'll find that the answer is x over 2 minus sine 2x over 4 plus c. And when you reduce sine 2x as 2 sine x cos x, then you can rewrite the same answer as x over 2 minus 1/2 sine x cos x. The half comes in because this part will have 2. So 2/4 is what is giving us a half. And also in a similar way, you should be able to say that if you use this expression for cos squared, then the integral of cos squared x dx will be the same as the integral of 1/2 into 1 plus cos 2x, which will give you this expression. And then you can reduce sine 2x in terms of sine and cosine, and that answer is the same as this form. So if you are asked to find the value of integral of sine squared, you can either give this as your answer or you can use this as your answer. All of them are still the same thing. And if you are evaluating the value of the integral of cos squared x, this can be the answer, or the same answer can be written in this form. So cases whereby the powers of sine and cosine, all of them are even numbers, then they're the ones which requires you to remember these identities in this slide. But cases where any of the powers is odd, is very direct, it's just application of this. Yes. I'm too slow.
You are too fast.
Okay. So where have I lost you?
From the start.
Okay, you
Yes.
Can you go back please to the page?
What time did you join? What time did you join?
Exactly.
From the beginning. Sir, please can you just go back to the previous page?
Okay.
Sir, we are not understanding anything.
Say I am not understanding many things, not we are. You may be the only one.
Oh, they are not understanding.
Go back to the previous page.
Okay, let's go back. Let's go back. There's no problem. That's why I'll be paid. So I say that the objective is to discuss how to evaluate integrals involving trigonometric functions. And
Not from the start.
Bas,
Next.
okay, so the best way for us to move on the same line. So please don't watch. I'm the only one who is allowed to watch when I'm presenting slides. But ensure that you have a pen. We cannot actually be on the same page if you watch like me. So I hope you have a pen and a book where you are.
Yes, we have.
Yeah,
okay,
so the best way for you to actually follow what is happening here is to have a book and a pen. So
Yes.
the key, what we are doing here is to discuss integrals. First class of integrals we are dealing with are integrals of this form. So you need to write in your book this general integral. So integral of sine power mx cosine power nx dx. So where m and n are whole numbers. So that's what we need to write. Have you written that integral?
Yes.
Yeah, so the best way for us to be at the same page, you need to listen and write at the same time. So the integrals we are dealing with in this section or in this lesson is the integrals of this form: sine power mx cos power nx dx. And because we are still young, the powers which we are dealing with are strictly whole numbers. So rational powers are beyond the scope of this class. So the powers m and n are whole numbers. So 0, 1, 2, 3, 4, etc. So not fractions. Tuko pamoja hapo?
Yes.
Sawa.
Is
Good. So then now when we have such kind of integrals, then there are many possibilities that this power m and n, either all of them can be odd numbers, or one of them can be odd, another one can be even, or all of them can be even numbers. Are you able to see that? That if you have two, if you are dealing with two whole numbers, the structure of this integral, there are three cases. One of the powers can be odd, another one can be even, or all of them can be odd, or all of them can be even. Okay?
Yeah.
Good. So we give the first example to evaluate the integral of sine power 3x dx. So when the power of the sine function is an odd number, you split that function as a product of two. So sine power 3 is split as sine squared and a sine function. So then now, that's what we are doing here, that sine power 3 is the same as sine squared, then times sine, then dx. And you recall that sine squared plus sine squared x plus cos squared x is given by 1. It's a very famous identity in trigonometry right away from high school. So which means that the place where we have sine squared, you are allowed to replace by 1 minus cos squared x. So this is what I've done here.
Excuse me.
Yes?
I can't see what you are saying in the screen right now.
Are you able to see the screen?
I have not
It's not
able to see
moving.
the
It's not
screen
moving.
is not moving.
Oh.
What you are saying is not moving the screen.
Are you able to see what I'm projecting on the screen?
No.
Yes.
It is still at
Is anyone having the same problem?
It is still at the first page where we started.
Oh, yeah.
So what are you saying? The person saying we are still where the first page where I started from. What are you seeing on the screen?
We can see the screen. We can't see what you are explaining.
Yes.
We can see.
Okay, the question is, what are you seeing on the screen? That's what I'm asking.
The part which you has the trigonometric integral.
Yeah, your thoughts are hanging.
Yes, sir. We are in the page of odd power of sine x.
Slide number?
Number 2.
3.
Yeah, we can see now.
So 2, 3.
3, yeah, 3.
Okay. We need to be on the same page. So I'm sure that you are seeing 3. So I'm at page 3.
Yes. 3 over 21. That page.
3 of 21. That's where I am. Is everyone at page 3 or there's people who are still page 1?
Okay now.
Page 3,
Yeah,
yes.
we are there.
Yeah, so we are on page 3. That's good. So sine power 3 can be split as sine power 2, then sine function. Are you able to see my cursor?
Yeah.
Yeah. So then now, sine squared can be written as 1 minus cos squared. That one everyone knows, okay?
Yes.
And then we multiply by this sine x dx. I hope up to at the end of that first equation, everything is making sense.
Sure.
Good. So then once you have done that, then you make the substitution in this bracket where this cos function replaced by u. So you use the substitution, let u be cos x. And if u is cos x, then you can find the u in terms of dx. So the u will be minus sine x dx. Are we able to see that?
Yes, yes.
Yeah. So then now, you now use this du and the u function to retransform this integral in terms of this new variable u. So where there's cos squared, you replace by u squared, and then where the sine x dx is negative du. I hope that will make sense from this this equation here.
Yes.
Yeah. So you can either make here dx the subject, or you can clearly see that sine x dx, when you multiply both sides by -1, so sine x dx is the same as negative du. So that's why I have this negative here. So then now you see this now will be simply an integral involving the variable u, which can easily be evaluated using integration by power rule. So power rule is what is giving us negative u plus u power 3/3 plus c. Able to see that?
Yes.
Good. So then now you remember now to replace the u by u with cosine of x the way it was given from this stage. So therefore the integral of sine power 3x dx will be cos power 3x over 3 then minus cos x plus c. Is that speed okay, or is still too low?
We are okay.
How with that example one?
Excuse me, sir.
It's understandable.
Good. So then now, before we give the second example, so that's why I'm saying that we discuss different cases.
Where did the negative?
So different
behind
cases of integrating integrals of the form sine power mx times cosine power nx dx. So there are only three cases. First case is when the power of sine is an odd number. And when you find the power of sine is an odd number, then what you do, you split that sine as a product of two functions. So where one part will be sine x, then the other part will be sine power the original odd number minus 1. So you know when you subtract 1 from an odd number, you must always get an even number. As always, that's a trivial result. So you split the sine power mx as two products, where one of them will be an even power, then the other one will just be sine x. So if you have done so, then the part which has the sine raised for an even power is the one that will help you to replace in terms of cos squared, because 1 minus cos squared x is always the same as sine squared x. So you replace that part with the 1 minus cos squared x, and then make use of the substitution u equals to cosine of x. So that substitution will transform everything in terms of the variable u that you can easily integrate using the substitution method, using the power rule. Similarly, when the power of cos is an odd number, then you will take that cos function in the product, you rewrite it as product of two functions, cos x times another cos function to power even number, depending on what the original power was. Then the part where we have the odd power is where you'll use the identity 1 minus sine squared x is cos squared x. And in a similar manner, you replace now your u as sine of x, the variable which is inside the brackets. Then that will help you to transform your original integral in terms of u variable, which you can integrate using power rule. And then that works for, you can use 1 or 2 when all the powers of the product sine and cos are odd numbers. But the last case is when both the m and n are even numbers, are even. So in cases whereby the powers m and n are even, you make use of the reduction formulas, which we derived in the previous class. So those are just general cases to consider. Then we will give examples to see how you are supposed to deal with each case when you have the actual problem to solve.
Excuse me, what about if both are odd?
If both are odd, you can either use case 1 or case 2. So case 1 or case 2 will be applicable to, you can either decide to go with case 1 or case 2 when all the powers are odd numbers. All of them will lead to the same answer.
For example,
if you have the integral of sine power 3x cos power 5x, you should be able to either use case 1 or case 2 to get the same answer.
Sir, if you apply that case 1, the same question, can you apply case 2 in the same?
Not clear.
So then now we consider the integral of sine power 4x times cos power 5x dx. So we see that one of the powers is an odd number. So the power of cosine is odd. So which means that that will be our reference function to help us to transform the integrand into a solvable form. So cos power 5, you write it as a product of cos power 4 and cos x. So cos power 4 x times cosine of x will still give us cos power 5x. And that split is to enable us to transform this integral in terms of an integral which you can easily solve by the previous methods we have discussed earlier on. So when we write cos power 4x, you should be able to see that it's the same as cos squared x power 2. So the place of cos squared, you replace by 1 minus sine squared. And then there's a power 2 because we had 4 here. Then you multiply by cos x times dx. I hope that line makes sense now.
Yes.
Good. So then immediately you make use of the identity 1 plus 1 equals to cos squared plus sine squared. Then what is inside the brackets, like here in this case, is what will inform you to fix as your u. So therefore you fix this part sine x, you let it to be your u function. So u equals to sine x means the u is going to be cos x dx. Then with this u and the u, you should be able to transform this integral in terms of the variable u. Because the place of cos x dx, you replace by du. The place of sine x, you replace by u. So which means the given integral is simply u power 4 into brackets u minus 1 minus u squared square du. Then it's not very hard to see that when you square 1 minus u squared, then you multiply by u power 4, you get this one. U power 4 minus 2u power 6 plus u power 8. Then the next step is now to integrate each part using power rule, and you get u power 5 over 5 minus 2 u power 7 over 7 plus u power 9 over 9 plus c. Then you substitute your u with sine of x, and this will be the final solution. That one makes sense.
Yeah.
Good.
Yeah.
So that's the case where the power of cosine is odd. So these are the, just as I recall, these are the reduction formulas we derived in class, where we have sine power n and then cos power n. So let me know when to scroll down. If you have finished copying, then you let me know so that I can scroll down.
Yes, next.
Good. So the next one is to evaluate the integral of sine power 4x dx. So you will realize that in this case, sine power 4, the power is an even number. And you see the same thing if you want to maintain the general structure, the same as sine power 4x, cosine power 0, x dx. So 0 and 4, both of them are even numbers. So in case of even numbers, like in this problem, is where we make use of the reduction formulas involving sine and cosine. So sine power 4 means n is 4. So when you replace n for 4 in this formula for sine power n x dx integral, then I have negative 1 over 4 sine power 3x cos x, then plus, then 4 minus 1 is 3, so 3 over 4, then integral of sine squared x dx. So that is what is happening in this question 3. At the place of n, we replace by 4. So when we replace, when we reapply the same reduction formula 1 with n equals to 2 to get the value of this integral for sine squared x dx, we get sine squared x dx is minus a half sine x cos x plus a half integral of 1 dx. And I hope you should be convinced that the answer given in equation 4 is convincing from the reduction formula.
Yeah.
Good. And then you know that we were dealing with sine power 4x, and so we had this 3 over 4, then another integral of sine squared here. So what we do from equation 4, replace the answer in this equation 4 for this part involving the integral of sine squared. So which means the final integration of sine power 4x will be minus 1 over 4 sine cubed x cos x. Then when you take 3 over 4 times minus a half, that's what is giving us minus 3 over 8. And when you take 3 over 4 times a half, is what is giving us 3 over 8x then plus c. So this is the final answer now for the integration of sine power 4x dx. So then you let me know when to scroll down. So
Let's
here
go.
we are just saying that there are many from our previous discussion. We say that there are many ways you can play with this with these trigonometric identities. So this answer we are getting here can as well be written in this form. If you interpret sine power 4x as the integral of sine squared times another sine squared, and sine squared can be given as a half into 1 minus cos 2x. So that's what's giving this other form. So you can as well express sine power 4 as sine squared times another sine squared, and then use that identity relating the sine squared function and cosine function to get this expression, which will be involving double angles. So either of them will be accepted as the answer to the integral of sine power 4x dx. So if it's okay, then you let me know to stall.
Go on.
Can I stall?
Yes.
Okay, good.
Wait a
So
minute.
here we are, this slide is just giving the summary of some useful identities involving the cosine and sine function. So these are our, all these four relations, we derive them in class. That sine squared can be given as a half into 1 minus cos 2x. Cos squared x can be given as a half into 1 plus cos 2x. Then sine 2x can be given as 2 sine x cos x. Then cos 2x can also be given as cos squared x minus sine squared x. All these things were done in class. So this is just a recap summary of the identities for sine and cos. So this too just illustrates how you can get the answer for the integral of sine squared and cos squared in two different ways by making use of these identities. So if you decide to interpret sine squared x as a half into 1 minus cos 2x, then when you integrate this sine squared x, this will be your answer. Then the same answer if you express sine 2x as 2 cos x sine x can be written in this form. So these and these are exactly the same thing. Similarly, you can interpret cos squared x as a half into 1 plus cos 2x. Then when you integrate, you get this. And the place of sine 2x can be replaced by 2 sine x cos x. And then this is the same solution. So if you are done, you let me know.
Next.
Okay.
Roger.
Okay, fine. A minute, please.
Song.
Yes, yeah, we're done.
Okay, good. So then now let's
We're done.
see
We're
the
done.
case where both the powers are even numbers. So when the powers are even, you try to rewrite the integrand in such a way that we have same type of trigonometric function. So for example, you decide to express everything in terms of sine function, or you decide to express it in terms of cos function. So for instance, we know that sine squared is given by 1 minus cos squared x. So the place where we have sine squared, you replace by 1 minus cos squared x. And then you retain this one as your cos power 4x. So by that substitution of sine squared with the 1 minus cos squared, you see that the integral will be transformed purely in terms of the cos function. Because now we have question, yes?
Yes, we need to replace sine squared x with 1 minus cos squared x over 2.
No. So remember sine squared, there are two ways of expressing sine squared. You can either express it in terms of cos function, or you can express it in terms of cos 2x, or you can write it in terms of the cos squared. So what you are trying to do here when you are dealing with the even powers is to have uniform trigonometric function in our integral such that the resulting integrands can be evaluated using the reduction formulas. So yes, it's true what you're saying, that sine squared can be written as 1 minus cos 2x over 2. But then when it comes to product of sine and cos and involving both even numbers, we make use of the substitution before we start evaluating the integral 1 minus cos squared.
Okay.
Fine. So when you do that replacement for sine squared, we'll have this. So the final integrand will be cos power 4x dx. And then when you multiply cos squared and cos power 4, you get cos power 6. And then now you see this part which has cos power 4x alone, you apply the reduction formula to work its solution. Similarly, this part which has cos power 6 x dx, you use reduction formulas for cosine power n function. Then with those two answers, you bring them together to get the final result. So the first step of the reduction formula for cos power 6 will have 1 over 6 cos power 5x sine x, then plus 5 over 6 integral of cos power 4 x dx. So what is happening here is that we are making use of this formula we have here in this slide, that the cos power n x dx integral is given by this formula. So the first step, when you are integrating cos power 6 x dx, you replace where there's n by 6. So this is what is giving us this was giving us this first solution. So you can as well now have the integral of cos power 4 x dx plus 1/6 integral 1/6 cos power 5 x sin x plus 5/6 integral of cos power 4 x dx. Or if once you have done this first step, you can call this one equation 1, and then you also reapply the same reduction formula to this function cos power 4 x dx. And then when you apply the reduction formula to the integral of cos power 4 x dx, there will also be a part where we'll have now cos squared x dx. Then with the integral of cos squared x dx, you get its answer from the previous steps we have shown. Then you bring all of them together. So when you bring all the terms for those three parts of the integration by reduction formula, you should be able now to get the answer for cos power 6 x dx, and then together with this cos power 4 x dx, bring them together with the proper sign the way it is given here, and you should be able to get the answer to this problem. Are we communicating?
Yeah.
So when you continue this all these steps, then you should be able to combine everything together to find the final answer. So what matters here is to get the key things what you have to do. And from the experience of the first three examples, you see that the direct integral which doesn't give you trouble is of which type? Odd. Yeah, odd is very easy to deal with. But for the even powers, then there's some extra work, because the first thing you have to do is to transform the integrand purely in terms of either cosine or sine. And then number two, once you have done that, then you have to apply reduction formula step by step. Then once you have the answers, you bring things together to get the final answer. But for the odd power, if we have any of the powers to be odd on sine or cos, then things are very direct. Good. So if you do everything correctly, then you should get the final answer at this.
Yeah.
So these are also other standard integrals which we did earlier on. But just as a recall, that if you're asked to find the integral of tan x dx, you rewrite tan as sine over cos. Then you fix cos to be u. Then with cos equals to u, then the u will be negative sine x dx. So with your du and du, you can easily transform the integral in terms of this new variable u, and you'll get negative ln of cos x plus c. But because from laws of logarithms, you know that if I have m ln of a, the same as ln of a power m, then this negative can be removed from where it is to be a power of cosine of x. And when you say cos x power minus 1, is simply the same as 1 over cos x. And 1 over cos x is nothing but sec of x. So that's why we usually say that the integral of tan x dx is ln of sec x plus c. So let me know if I can scroll.
Let me see. Also, please.
So once you're done, you let me know to when to scroll.
Can scroll.
Okay, fine. So the other standard integral is.
Wait, Jack.
Okay, fine.
Scroll, mwalimu.
Kindly go back to the previous slide.
Wait.
No, we will send the notes after the class, so we don't have to go back and forth. So the other standard integral is the integral of sec x dx. So to work out the value of the integral of sec x dx, we make use of the substitution u equals to sec x plus tan of x. I think also this example I did it in class. This is just a repeat of the same things we did in class. So you multiply this sec x by sec x plus tan x over sec x plus tan x. You substitute u by sec x plus tan x, which when you define your du, you'll get sec x tan x plus x squared x dx. And then it is not hard to see that this transforms to sec x u dx, which you have du over u is sec x dx. Then with the substitution, then the answer is obvious. So similarly for the functions involving sec and tan, when you have sec power m, tan power n, can be done in similar ways. So I'll give a break of 7 minutes, and then I'll come to finish in the next 30 minutes. So I'll share these slides after the class, so you don't have to worry. I'll share. If you didn't like it, I'll reshare this.
I have a question.
Ask.
Is there in sec x plus tan x, why are you saying du is equals to that? Why I say u is equal to sec x plus tan x?
Why are you in class last lecture?
Yes, I'm saying.
Yes.
Why are you saying u is equal to sec x plus tan x?
Yeah. That's I'm also asking you. Why are you in class last lecture?
Yes, I was.
Yeah. So what is happening here? We sometimes we have to be very smart when you are solving these problems. So to solve the integral of sec x dx, we don't know the definite answer, but we try to see how we can manipulate the integrand so that we doesn't lose the meaning of the function itself as sec x, but at the same time, we get a form which we can easily integrate from the previous methods we have discussed. So what is happening here is that when you write the integral of sec x dx, so in the evaluation process, which I have not written in this slide, I will write integral of sec x dx is the same as integral of sec x times 1 dx. So I multiply sec x by 1. And I hope we agree with you that multiplying a function by 1 does not change the value of the function. Yeah.
Yes.
Yeah, so when you multiply
Yeah.
1 by a function, the function remains the same thing. So that one, I write it in smart way as sec x plus tan x over sec x plus tan x. I hope what I'm saying you are writing. Whoever asked the question. So I'm describing where the sec x plus tan x came from. That you write the integral sec x dx as sec x times 1 dx. You have not changed the integral itself. Then that product you are saying times 1, you write it as sec x plus tan x over sec x plus tan x. Mandika?
Yes, yes.
Then can you
Yes.
multiply the numerator and tell me what is the new function now? When you multiply through, the numerator will give you? When you multiply now, we said sec x times 1, and that one you're writing it as sec x plus tan x over sec x plus tan x. When you multiply the numerator, what will be your new numerator? What will be your new numerator? You can help him.
1 over sec x plus tan x.
Pana. Remember, we have the sec function times the fraction sec x plus tan x over sec x plus tan x. What will be a
1.
new numerator when you multiply through by sec x?
One.
X squared x plus
Sec
tan
squared x
plus sec tan x.
plus sec x tan x, correct. So when you multiply through, you get sec squared x plus sec x tan x. Good. So then now, your new integrand will be sec squared x plus sec x tan x, everything over sec x plus tan x. Are we there? For those who are following.
Yes.
Yeah. So that's now where we say now, let u to be sec x plus tan x.
Sure.
Then, so once you have your u equals to sec x plus tan x, then you get du. So du, when you differentiate sec x, you get the derivative of a sec function.
Sec x tan x.
Sec x tan x, correct. Then plus derivative of tan x.
Sec squared x.
Sec squared x, correct. So this is where I got this answer from. That's where this answer came, why this answer came in. So then now you can, where we have sec x tan x plus sec squared x dx is our du. And you remember previously, our numerator was sec squared x plus sec x tan x. So when you make dx the subject here, you should see where the whole bracket is going, why the bracket cancels out when you make dx the subject, and you substitute accordingly. This can only make sense if you are writing, not listening. If you are listening and writing at the same time, is when you can see where what I'm saying. That when you make dx the subject from this, then you substitute back where you are coming from, you'll find that everything involving x will cancel out. Are you seeing that? But the x will be the same as du over sec x tan x plus sec squared x. Then when you replace back, the whole original numerator will cancel out with this bracket. And where we have sec x plus tan x will be u. And so therefore it just be the integral of du over u. You know, Mekana?
Yeah.
Yeah, good. So then now, that's where now we are getting the ln of u plus c. So whoever asked the question actually asked a very valid question. The way these things are behaving, sometimes they are missing. So where if someone asks you, where did you get now? Why would go to sec x plus tan x? Why not any other function? The answer or the goal is that we are trying to play with the integrand so that we find a function which you can easily integrate without struggling. So that is the choice that we pick. So small break. So the same. So this is still a continuation when we have. I told you to get the derivation for the integral of tan power n x dx. So when you get the reduction formula, then you should be able to solve also this kind of problems, and also products of sec and tan. So a small break, then we'll come back to wind up.